The last video we have seen a temperature distribution of heated rod for all times. That is exactly, so if you are given a rod with initial temperature, how the heat is diffusing in that rod over a time. So that is what is the meaning of finding a solution for the initial value problem for the heat equation of over a spatial domain, that is from minus infinity to infinity. Okay, in this video we will try to see if you are given a rod, infinite rod, one dimensional rod, okay, one dimensional rod with the initial temperature distribution. So let us say initially you know the temperature of the rod throughout, and it satisfies the heat equation, and the boundary condition at one end you are fixing the temperature either 0, you fix the temperature as 0, or you insulate it the end point. So that is what, so you have two initial boundary value problems, okay. So for the heat equation, so we will just define and try to solve it just based on the solution that we derived in the last video for the infinite rod, that is occupying minus infinity to infinity. So let us see what are those semi-infinite rods. So if you have a heat equation on semi-infinite domain, so heat equation, or let us say initial boundary value problem. So let us say heat equation is this: ut minus alpha square utt uxx equal to 0. Now x is only positive, so that is 0 to infinity. So you have infinite rod with an end, one end is 0, other end is simply you have a infinite rod. So you have infinite rod, other end, so the boundary is only this one. So initially you know the temperature of this, so u at x0 is actually given, so that is given. So this is the initial data, and this boundary data at this point you have a boundary data, that is u at x is 0, and for all times you maintain either 0 or you insulate this also. So you do not allow the heat to pass from this end. So if you do that, that is because this is the x axis, so the normal velocity, normal derivative has to be 0. That is a flux, that is a flux going out, okay. So that should be, so derivative with respect to x at, so dou u by dou x at 0 t equal to 0. So either this or this, okay. So we have seen when this kind of boundary condition, we know how to do it. So when you look back into wave equations on semi-infinite string, so what we have done, when you attach the string with displacement is 0 at the boundary for all times, then you know that you have to extend those functions involved as an odd function, so that if you extend as an odd function, this boundary condition is automatically satisfied. If you attach the string with this condition, that means there you allow it to be free, ux is 0, okay. So there what happens, you extend as an even function, and so that the boundary condition is automatically satisfied, and we made use of D'Alembert solution, and then that is over the full real line. So we made use of that solution and give you the solution for the semi-infinite string vibrations for the semi-infinite string. So we do the same thing here. So now instead of the string, you have infinite rod with the initial heated rod. So at time 0 you have some temperature, and you want to see how it diffuses along this, how the heat is diffuses, that means how the temperature changes over a time in this rod, semi-infinite rod. So the initial conditions we write, so ux, initial condition is this, you have x0 equal to fx, and x is positive, and the boundary condition is u at 0 t. So let us start with this initial boundary condition. So you have, this is the initial boundary value problem for the heat equation on the semi-infinite domain, x positive, and is also t is involved, that is the time t positive, okay. So how do we find this solution? We just we make use of because of the boundary condition, since u at 0 t equal to 0, we extend u of x t as an odd function in x as an odd function of x. So, that means I define a new function u1 of xt as, if x positive, you take same u of xt. So, that is satisfied by the heat equation, and otherwise for x negative you just do it as an odd function. So, that is u of minus xt. So, when x is negative, minus x is positive. So, that is u of positive quantity t, that is actually what we have already, that is the same. So, if you extend it like this, okay, so what happens at 0? So, at x equal to 0, so what happens u? So, if you do like this at x equal to 0, it has to be so if it is a odd function, so if it is odd function, that means u at minus x, u at xt equal to minus u of minus xt for x negative. So, that is what is the meaning, okay, or u1 is this one, that is actually equal to u1 of minus xt. Okay. So, what is the u1 at u1 at xt, x negative is minus u minus xt. Okay. In terms of this, if x is negative, minus x is positive. So, that is same as minus, when minus x is positive, u1 when x is positive is u of xt, u of minus x is positive. So, that is what is the same. So, both are same. Okay. So, that means it is 0. So, now once you put x goes to 0 here, so you put x equal to 0 here. So, this will give put x equal to 0. So, you see that u1 at 0 t is same as minus u1 at 0 t. So, that means this is possible only if 0 t equal to 0. Okay. So, what you have is this is simply 0 at this value at x equal to 0, and similarly you extend. So, you need initial value even for x negative. So, you extend, to get that you extend this initial temperature also as an odd function. So, extend fx as an odd function, So, you get you write this as a odd function is f1, that is fx if x is positive, and 0 if at x equal to 0, obviously because it is odd function, minus f of minus x if x is negative. Okay. And the way you do it for x positive is anyway satisfying the heat equation. For x negative, if you do twice, if you do, so u1 x negative, what is the t derivative is minus ut minus xt, okay, and then plus if you do twice x derivatives of this, 2 x derivatives of minus u of minus x is again minus 2 derivatives, one derivative will get 1 minus 1 times u x of minus xt. If you do one more derivative with respect to x, that will be 1 more square. So, you get this is simply minus is common, this will be plus. So, ut of minus xt plus you have alpha square. Okay. Just try to add, okay, put it in this, if you multiply with alpha square uxx minus xt, this is x minus is common. So, this is for x negative. So, x negative means minus x is positive, and minus x is positive, this already satisfied the heat equation, that is what is given problem. So, this is equal to 0. So, you see that u1x is satisfying, this implies u1 of xt satisfies the initial value problem. Okay. So, that is u1 t minus alpha square u1 xx equal to 0. Now, this is defined for everywhere. So, this is this one, and u1 at x0 is nothing but here fx, this is fx minus u of minus x. Okay. What is that one? So, at x equal to 0. So, this is exactly, you can see that this will be u1 at x0 is u of x0, that is fx when x is positive, okay. And then what happens when x is negative? So, when x is negative, then this becomes minus u of minus x 0. So, when x is negative, so when x is negative, minus x is positive, this is nothing but f of minus f of minus x, okay, because minus, as it is minus u of minus x 0, when x is negative, minus x is positive. So, that we already know that is f of minus x. So, this is what you have. So, this is nothing but now it is an odd function. So, that makes it x is at x equal to 0, this has to be 0. So, this is nothing but your f1 of x, okay. So, for every x belongs to R, this is true. So, this is the initial value problem which we solved in the last video. So, you can now write your u1 of xt as the solution. So, which we know what exactly is that solution you have here. So, 1 by square root of 4 alpha square pi t, 1 by square root of 4 alpha square pi t, okay, and then integral minus infinity to infinity e power minus x minus y whole square divided by 4 alpha square t, 4 alpha square t. Now, here f1 of t, f1 of y dy. So, this is your solution. This is true for every x belongs to R and t positive. This is from the solution over the full real line for the heat equation with this initial data, okay. So, but you need u1 x t when you restrict x only positive side, that is exactly your u x t, right. So, to do this, so when x is positive, you have 1 by square root of 4 alpha square pi t, and this is from so this is exactly what you have. So, you have a 0 to infinity, you break this integral into 0 to infinity. So, what you get is e power minus x is only positive y square by 4 alpha square t, and f1 of y is now between 0 to infinity. So, that is f of y dy. Now, plus now minus infinity to 0, what you have is this is also this is same, this is x minus y square by 4 alpha square t. Now, f1 of y when y is negative, minus infinity to 0 is y is negative, that is minus f of minus y dy. So, this is what is the solution. Now, here if you change the variable y as minus y, if you replace y by minus y by minus y, then you have f of y, and dy becomes minus, so that is going to be plus y, and you have minus y you are replacing with y. So, you have minus y, so you are replacing with, so x plus y. So, this is what it becomes after change of variable. So, now y equal to minus y, earlier y is minus infinity t, and you have, so the limits will change to, so you have infinity to 0, okay. So, you have minus plus, so you get infinity to 0. So, let us say earlier what you have is minus y equal to y1, let us say. So, so if you put minus infinity, so y1 is minus infinity, y is minus infinity, minus is plus infinity. So, you have plus infinity to 0, this is what it becomes. So, if you now change these limits to 0 to infinity, you have a minus, you have to replace with minus. So, this is what you have. Now, this is only for x positive. So, this is your solution of the required initial boundary value problem, okay. So, you will do the same thing if you replace. Now, you consider this problem. So, the same initial value, take the heat equation with the same initial data, and now you consider this boundary condition. So, what you do is you similarly what we do is in this case when you have so let us do that one. So, if you have the problem initial boundary value problem with ut minus alpha square u x x equal to 0, x is positive and t is positive, and u at x 0 is f x, and u at 0 t, this one u x 0 t is 0. Okay. This is like you insulate that one end of the rod. If you insulate at this point, is also insulated. All along this we have insulated lateral things only, so that heat dissipation only in one direction. So, here also you insulate this end, so that it will not, heat will not go out. So, that is what is the u x equal to 0. So, you have semi-infinite rod again. So, you have, this is the initial value problem. So, in this case again, so when you have a problem like this, when your boundary condition is like this, so what you get is extend the functions, extend u of x t and f x as an even function, as even functions, How do we do this? So, start with u1 of x t as, this is the extended function, even extended function, as I am calling it, let us call this u2 because we used for odd extension as u1. This is the even extension, that is u2. If I call this u2, so what you have is uxt if x is positive. If it is even, what you should have is u of minus xt is same as this one. Okay. So, in this case you do not know exactly what happens at x equal to 0. Okay. So, this we do not know. So, this is clear. So, once you extend this, at that point you are not doing it. Okay. At one point you are not extending. Okay. So, this is still unknown. So, you call this you do not know at x equal to 0. So, earlier when you extend it, you know that if you extend as an odd function, you know the value at x equal to 0, but here it is not clear. So, nothing is known. Okay. But you know that because this is a even function. So, u x t equal to u of minus x t at x equal to 0, if you differentiate u x of put x equal to 0 is same as minus u x at minus x is minus g, that is 0 t. So, this will give you u x at 0 t equal to 0. So, this condition, boundary condition, is automatically satisfied now. Okay. You differentiate this equation because this is a even function, this is same, you both sides you differentiate with respect to x, what you get is this, and put x equal to 0. Once you put x equal to 0, you are evaluating u x at x equal to 0. So, you have this one. So, this will give me this boundary condition automatically satisfied. So, u2 satisfies. So, this implies u2 of u2 x at 0 t is automatically satisfied as 0, okay, for every t. And you can also extend, once you do this and f x is also you can extend as even function. So, you have f x x positive, f of minus x as x negative. Okay. So, once you have this one, so you call this f2, my even extension I am calling f2. So, what you get is, you can see this satisfies the wave heat equation already, and this is also satisfying. 2 x derivatives will not give any minus plus. So, this will also satisfy the heat equation. So, clearly u2 satisfies, now u2 satisfies the initial value problem, u2 t minus alpha square u2 xx equal to 0. Now, x belongs to full real line. Okay. So, you do not know exactly at x equal to 0. So, just one point. So, that is why it is full real line. So, okay, still call this, you call this itself, you do not know exactly what it is. Okay. So, you call this u2 at 0 t, you still do not know at x equal to 0. So, that is how you extend, your extension is like that. So, still this is just a point, it is just a fixed number, so that satisfies the derivatives. When you put it in these two derivatives is 0, it is satisfied even at that point. So, I included that point. So, x belongs to R. And what is the initial data? So, at 2 x2 x 0 is now, what is x2 at 0? So, x0 u x0 is f x x positive, and x negative, what you get is when t u of minus x 0, that is u of minus x means f of minus x. So, you have f of minus x. So, this is nothing but your f2 of x, okay. And again here, so it is still some constant f at 0, you still do not know exactly what it is, okay. And you do not know, this is some number. So, you cannot say it is f2. So, you call this u2 of x0, okay, u2 of 0 0 at x equal to 0, it is simply u2 of 0 0, that is simply constant. So, this is exactly your f2. So, if you want, you can write here also you can say u2 of 0 0 at x equal to 0, that is the number, you do not know, that is still arbitrary number. So, this is my f2. So, this will give me, so immediately, so we know the solution of this u2, because as in the last video I have solved for this initial value problem, we know the solution. So, you can write u2 of xt as a solution, what is that solution what you have? So, like this u2, so u2 is exactly 1 divided by 4 alpha square pi t under root, okay, and then you minus infinity infinity e power minus x minus y whole square by 4 alpha square t into f2 of y dy, because this is the integral, that point x equal to 0 does not matter, you are going to evaluate that f2 at 0 does not matter. So, if you break it, so integration at one point is always 0, okay. So, you need not consider certain points, finite number of points you can always remove in an integral value is same. So, this if you restrict only for x positive, that is exactly your u of xt, what is required function, what this is exactly is this, okay. So, this is for x positive. So, in this integral you have to consider only x positive. So, this will give me 1 by 4 alpha square pi t under root, and now this is from 0 to infinity e power minus x minus y, x is positive, y is now between 0, y is also positive, 4 alpha square t. Now, f2 of y when y is positive is f of y dy. Now, plus, now you do from minus infinity to 0, this is kernel is same, that is x minus y whole square by 4 alpha square t. Now, f2 of y when y is between minus 1, when y is between minus infinity to 0, that means when y is negative, this is f of minus y dy. Now, you do the change of variable here. So, what you get is x plus y, this is f y, and you have a dy is minus of dy, that is minus, this is going to be infinity to 0. So, when you write this infinity to 0 as 0 to infinity, this will become again plus. So, this is what is your solution, required solution. So, is the implies u is the required solution of the initial boundary value problem, okay. So, that is here. So, this is what you have. So, this is the initial boundary value problem. So, when you consider this rod with insulated end, what is the diffusion process for this initially heated rod, semi-infinite rod, okay. So, this is how you find the solutions, okay. How many minutes are there? A minute? Okay. 24 dacha. Another 10 minutes. 10 minutes. We will just try. So, this is how we solve on semi-infinite domain heat equation with initial data and boundary conditions. Okay. So, we will just give you the briefly what is the, we will look at the solutions what that we derived. Okay. So, for the infinite thing, so let us say what is the solution, what you have is earlier if you just look back, when you look back your solution is this one. So, that is, let me write this as so let us go back to this problem. So, u t minus u alpha square u x x equal to 0, x is full real line is infinite rod with the initial data as f x, x belongs to R. So, this initial value problem has a solution, this has a solution u x t as what is the solution you have got? You have derived the solution as integral minus infinity to infinity, and this is my s of x minus y phi y dy. Okay. So, where x is s of x, and this is right. So, this is s of x minus y comma t and f x f of y dy, where s of x t is actually equal to 1 by 4 alpha square, that is square root of 4 alpha square pi t. So, this is into exponential minus x minus y. So, you are replacing x by x minus y. So, what you get is x square divided by 4 alpha square t. So, this is what is my s of x t. When you have x of x t, s of x minus y t is simply what you have is the solution that we wrote earlier. Okay. So, that is the solution we derived. If you actually see this one, so in the, if you know the probability theory, so there you can write you have this kind of curves in the probability theory. If you have this 2 pi alpha square rather sigma square e power minus x minus mu by mu square by 2 alpha square. So, if you know this this distribution, this is a normal distribution, this is the curve for normal distribution. So, that is my f of x. F of x is the this normal distribution curve. Let us call this some g. This is the normal distribution curve. Normal distribution is basically, if you see that this is like a bell curve, never touches 0, but this will be, this is how it looks. This is at x equal to mu, you have a peak. At x equal to mu, you have exponential function is 0, that is 1, and this is what you get. The peak is at 1 divided by, when x equal to mu, this line, this is my y line, this is my x. So, you get this point is actually 1 divided by root 2 pi sigma square. This is the peak you get at x equal to mu. Mu is the mean, and sigma is a standard deviation. Okay, the standard deviation of the normal distribution. So, if you have like this approximate width, you ignore this error, this length between this approximately is actually 2 alpha 2 sigma. Okay, 2 sigma, the length of this is 2 sigma. So, by using this one, so approximately the width of this bell curve, its peak is this, peak of the bell curve is this, and width of the bell curve is, so peak, the height of the bell curve, you can call this height of bell curve is 1 by square root of 2 pi sigma square, and width of the bell, width of bell curve if you see, this is actually approximately 2 sigma. So, make use of these things and apply here. So, this is also looks like such a bell curve. Okay. So, if you do that, what is that height? Height of this height of s of x t is at 1 divided by square root of 4 alpha square pi t. Okay, that's clear. So, that is true. And what is the width? Approximate width of s of x t. Okay, approximate width of this one. Okay, curve width, approximate curve width, positive curve width of s of x t. What you see is 2 times and what you get is 2 alpha root t. Okay. So, 2 times sigma is like root 2 here, alpha is here, root t. So, root t. So, that is what you have. Now, what happens as t tends to 0? As t tends to 0, so we are only going from positive side, t cannot be, so time is always positive. So, you are taking this limit from the positive. So, what happens? S at x 0. Okay. So, how does this look as a function? So, this geometrically, this what happens, the bell curve looks very, very steep at x equal to 0. So, mu is 0 here. So, here in this case x minus 0 square. So, at x equal to 0 you have infinite peak, this is actually peak will be infinite. Okay. So, you see that this is going to infinite and this width of this curve is becoming 0. This width goes to 0 and height goes to infinity. So, let us say height goes to infinity. This is what you are seeing. Okay. So, where do you see such curve? If you know a delta function is such thing. So, delta x, if I define it as 0 if x is not equal to 0 and not defined. So, the infinity at x equal to 0. Okay. Such is, this is not a function, this is actually limit of certain normal functions. So, if you think of delta x as a limit of usual functions. Okay. That is why it is called a generalized function, limit of, so this is called a generalized function. So, which you see it as a limit of usual functions. So, something like limit of all these usual peaks. Okay. So, usual like this every time you increase, but its integral value, okay, its area is same, we maintain the area as 1. Okay. So, if you maintain the functions f n of x dx equal to 1 from minus infinity to infinity. So, if you do like that, so what happens initially, suppose you have f1 is like this, f2 is you come inside and you increase the peak, so that its value is whose integral has to be n is from 1, 2, 3 onwards. This is my 1, this is my 2 and 3 and so on will go on, finally you end up finally some infinite thing. Okay. It's very steep peak, finally this is how it goes. So, this limit of is the usual functions as n goes to infinity is my delta function. So, that is the generalized function. So, you see that this is also behaving the same fashion. So, s of x 0 is actually my delta function. So, delta function. Okay. So, what is that delta function? So, s of x 0. So, that is the delta function. So, that is why your solution x y x t u of x t, which is from minus infinity to infinity, s of x minus y f of y dy. Now, what happens if x of x minus y comma t x minus yt f of y dy. This is the solution. Now you take this limit t goes to 0, okay, that is u at x 0. So you take this limit t limit, so that is y 0. So this is exactly minus infinity infinity. This is now delta of x minus y f of y dy. So delta function, when you multiply with a function and integrate, what you get is at earlier. So you have this is like a delta function, scaled delta function at x, translated delta function from 0 to y. So you get f at y at x, okay. This is the delta function of y translated to kind of y minus x you can write, okay. If you want you can write y minus x or x minus y, all are same, okay. So x minus y you can write, because x s of x minus y is this, you are replacing x minus y f of y. So this is symmetric, this is the limit of symmetric functions. So it does not matter if it is x minus y or y minus x. So it is a function of y, delta is a function of y. If you view y equal to x, this is infinity, that will give you exactly fx, okay. This is exactly my initial condition. So your solution is actually satisfying the initial data. If you think so, what you get is even that is like a delta function. So S is actually kind of delta function. So you have a bell curve as t goes to 0, your solution that involves s of x t, it looks like a bell curve. As t goes to 0, it behaves like those kind of functions, those curves finally eventually that converges to the delta function, okay. So we make use of this to interpretation and to finally to solve certain boundary value problems. For example, we'll do some more problems. For example, heat with source, okay. Let's do this one. So what we need, we will try to use this. Where do we use this? Let me put it. So we'll try, yeah. So we use this interpretation just to show you that we will try to solve the non-homogeneous heat equations, okay. So use the above interpretation. So to solve a non-homogeneous heat equation. So that is ut minus alpha square uxx. Now this is u is a function of xt. So the right hand side you have a forcing, you call this some h of xt, okay. So you have something like you have a heating. So outside you have a source, okay. So you are heating the rod from outside, some energy is coming inside the rod for all times, okay. So if you do this now between minus infinity to infinity and t is positive, how do I solve this non-homogeneous equation with the initial data u at x 0 equal to fx, okay. So to solve this non-homogeneous equation, so what we do is we try to write u of x t as u1 of x t plus u2 of x t like earlier. So this will solve the homogeneous equation with the initial data, and this solves the non-homogeneous equation with 0 initial data, so that it will solve. So we will see this one. So u1 satisfies u1 t minus alpha square u1 xx equal to 0, and then u1 at x 0 equal to fx, okay. So this we know how to solve. This is the initial value problem that we solved earlier last video, okay. So now I know this u1 of xt. So what happens to this u2 actually satisfies the heat equation alpha square u2 xx equal to 0 for x belongs to R, even here x belongs to R, okay. So and what happens here, u2 at x 0 initial data is now 0, sorry, now here this is actually satisfying u non-homogeneous equation. So h of x t, x belongs to R, so u2 of this, so that u1 plus u2, that is u, satisfies the heat equation, with so non-homogeneous heat equation, okay, with forcing h of x t. So, that what is mean, what it means is u1 ut, now just calculate ut minus alpha square u x x is actually equal to u1 t minus alpha square u1 x x, now plus u2 t minus alpha square u2 x x. So, this is equal to 0 and this becomes h of x t. I just split it into two problems. So, finally, this is actually h of x t. So, it solves, u satisfies the non-homogeneous equation, and u at x 0 is actually same as, if I define this way, u1 at x 0 plus u2 at x 0. So, what is u1 at x 0? That is f x, and this becomes 0. This is 0 because that is how I defined this problem for u2. So, this is actually f x. So, that what you have is this u, sum of these u1 and u2 actually satisfies the non-homogeneous equation. So, if you solve these two problems, this one and this one, that means you solve the non-homogeneous equation. This we already know, this we will try to calculate. So, we will just try to see this problem. So, u2 t minus alpha square u2 x x equal to 0 for x belongs to R and t positive, and sorry, this is a homogeneous non-homogeneous equation. So, this one and u2 at x 0 is actually equal to 0. So, with 0 initial, so initially you have a rod, infinite rod with the with heat is 0, but there is a heat coming from outside. So, that is what is this forcing. So, this forcing term. So, then what happens to the rod? So, this is what is we need to find, okay, find the solution of this. That means you find the solution of the non-homogeneous equation, okay. Once we find this, once we find the solution of this problem, then non-homogeneous problem, then non-homogeneous problem is solved, because I take this u2 and I add it with this solution of this problem which we already know. So, that will give you the solution. So, this is what we will see in the next video. So, we will try to solve this this initial value problem in the next video, along with using the method called operator method, okay. So, in the next video we will try to solve this initial value problem for this non-homogeneous equation with 0 initial condition using the operator method. So, we start with the simple ODE with it's something similar to this equation, ut minus some a is simply constant into u x x, okay, equal to 0. Then what happens, we will just by looking at the solution, we identify that the solution here, we try to construct, it is called the operator method. So, we will just see this in the next video along with other possible problems that can be solved, okay. Thank you very much.